Hi, my name is Matt. Today I'll be explaining how you do the second derivative test. Um, First of all, you start out with the original function. We have it here: f of x equals 2x to the third minus 3x squared minus 36x plus 100. First thing we need to do is take the derivative of this original function. So it would be 6x squared minus 6x minus 36. The reason we do this is because the first derivative test is how we find our critical points, which you'll see will come into play later with the second derivative test. So now we can factor out a 6 out of each one of these terms. So now our function becomes x squared minus x minus 6. Okay, and now we can factor this, which it would become 6 x minus 3 x plus 2. Okay, and now we can see that we have two critical values, or we have two critical values here at x. So one will have x equals 3, at the other one will be x equals -2. Okay, now we come back up here and we take the second derivative of this function. So this would be f double prime of x 12x minus 6. Okay, now this is where the actual second derivative test comes into play, because we have to evaluate the second derivative at both of these critical values. So we'll do that f double prime of we'll do 3 first. So f double prime of 3 equals 12 times 3 minus 6. So this will equal 12 times 3 is 36 minus 6, and this equals 30. So by our rules, we know that when the second derivative is positive, it's concave up, and if it's concave up, that means that the concavity is like this, which means that we would have a local minimum here. So we'll evaluate the function at f of -2. We'll do the same thing, we're just plugging -2 in for x. So 12 times -2 minus 6. So 12 times -2 is -24, and minus 6 will give us -30. So this tells us that it's concave down, and that we have a local maximum at x equals -2. Okay, now that I've showed you how to find local maximum and local minimum using the second derivative test, now I'm going to show you why it's also necessary to do the first derivative test, because there is an exception to the second derivative test. If one of our critical points would equal 1/2, and we would evaluate the first or the second derivative function at x equals 1/2, it would be f double prime of 1/2 equals 12 1/2 minus 6. Now you can see this will evaluate to 12 over 2 minus 6, which eventually 12 divided by 2 is 6, so we have 6 minus 6, which leaves us with 0. And before we said that if the second derivative is positive, it's concave up, and that means we have a local minimum. And if the second derivative is negative, that means that it's concave down and we have a local maximum. But now it's neither positive nor negative, so we have a special exception. So this means that we have an inflection point. An inflection point is when a function switches from concave up to concave down. And when the second derivative is equal to 0, that means that we have an inflection point. It also proves that the second derivative test is inconclusive in proving whether or not this value of x is a local minimum or a local maximum. And to prove that, you would need the first derivative test.